In a bustling manufacturing plant, a team of engineers gathered to address a rising issue: defects in their products. They turned to Pareto analysis as a solution. This method would help them identify the most frequent defects and effectively eliminate them. One engineer stepped forward, explaining the principle behind Pareto analysis. "Imagine if we could focus on just a few issues causing the majority of our problems," she said, pointing to a graph displayed on the screen. The chart illustrated how certain types of defects were far more common than others. Using this analysis, they discovered something surprising. 80% of the defects came from only 20% of defect types. They realized that if they could tackle these specific issues, they could dramatically reduce the overall defect rate. For instance, defects related to faulty wiring accounted for a significant portion. By focusing their efforts there, they could see immediate improvements. The team decided to regroup weekly to investigate these key areas. They explored the root causes, asking, why did these defects occur? In one meeting, they discovered that a particular machine's calibration was often off. By adjusting its settings, they hoped to solve a major problem. As the weeks passed, the team monitored their progress. With each improvement, they celebrated small victories. They reduced defects related to faulty wiring by over 50%. These efforts showcase the power of targeted action through Pareto analysis. They learned that by identifying and eliminating assignable causes, they could enhance product quality and boost overall efficiency. We explore variation in processes. The top section shows common cause variation for process A, where the handwriting is consistent, suggesting stability. Below it, process B demonstrates a similar pattern, indicating that both processes have inherent variability caused by common factors. The last section highlights assignable cause variation in process C, where the handwriting is noticeably different. This change signals that something specific has influenced the process, leading to a shift in distribution. Understanding these differences is crucial for analyzing data and improving processes. A control chart is a visual tool often used in statistics and quality control. It helps to monitor a specific process over time. This tool can show how the process behaves and identify any variations. The sample size and sample frequency refers to how many samples you take and how often. Sample statistics includes important values, such as sample mean, average, sample range, the difference between the highest and lowest values. The center line represents the average of the sample statistics. It is crucial for understanding how the process usually operates. Control limits are the upper and lower limits of the chart. They help identify whether a process is in control or not. The upper control limit is typically set at 3 standard deviations above the mean. The lower control limit is set at 3 standard deviations below the mean. In a normal distribution, about 99.7% of all measurements should fall within the control limits. If measurements exceed these limits, it may indicate an issue. This could be due to special causes that need further investigation. The control charts showcase an X-bar chart and R chart for the Zuter steer support height measurements. On the X-bar chart, we see fluctuations over time. Each data point represents the average support height from a series of measurements. For example, a noticeable rise in average height occurred around the 14th day, suggesting a potential shift that requires further investigation. The R chart, on the other hand, focuses on variability. It highlights the difference between the highest and lowest values in each sample. This gives insight into the consistency of the measurements. For instance, a wider range observed in the 19th day indicates greater variability that might need attention. Together, these charts provide a clear narrative. The X-bar chart reveals trends, while the R chart captures consistency. This dual analysis is crucial for monitoring and ensuring quality in production processes. In robust design, we face the challenge of dealing with process variation. Sometimes, it feels like there's no way to lessen this variation. This can lead to concerns about producing defects in our final products. However, this doesn't mean we are stuck or doomed to failure. Instead, we can explore different strategies to manage and accept variability, ensuring we still achieve quality outcomes despite the challenges. In the pursuit of quality, tackling variation is crucial. When reducing defects becomes a challenge, the focus shifts to altering the design of a product or process. This means making adjustments so that the original specifications can be relaxed, without sacrificing quality. For instance, consider a manufacturing process for a smartphone. If the components vary slightly in size, instead of tightening the specifications, designers might innovate the assembly process. They could incorporate flexible materials that can absorb these variations, ensuring that the final product remains functional. Another example is in the automotive industry. Car makers often face challenges with engine performance due to variations in fuel quality. By designing engines that can adapt to a broader range of fuel properties, manufacturers can ensure smoother operation. This approach helps in accommodating the inherent variability in fuels, rather than strictly controlling every aspect. One effective methodology to facilitate robust designs is called Design for Six Sigma. This approach offers a set of tools that guide engineers and designers in creating products that not only meet specifications but also withstand variations. It emphasizes proactive design changes rather than reactive fixes. Six Sigma is a method used to improve processes in a structured way. It focuses on reducing errors and increasing efficiency. Six Sigma is a data-driven approach and relies on data to identify problems and track improvements. The process includes 5 main steps: define, measure, analyze, improve, and control. This sequence helps teams understand and refine their work. A defect is anything that doesn't meet quality standards. Six Sigma aims to minimize defects to fewer than 3.4 per million opportunities. This target is known as 3.4 defects per million. It sets a high standard for quality. Six Sigma was notably used at Motorola. The company sought to improve its products and services, thereby increasing profits. Many companies, including GE and Boeing, adopted this method as a way to enhance performance. Companies that implement Six Sigma enjoy significant improvements. They operate more efficiently and provide higher quality products. Businesses benefit greatly when they prioritize customer satisfaction and minimize defects. If you enjoyed this content, please consider liking and subscribing. Thank you.